Will tell us about a grounded conceptual modelship for ownership in Rust.
All right. Hello, everyone. My name is Will Crichton. I'm a postdoc at Brown, and this is joint work done with Gavin Gray at ETH Zurich and my postdoc advisor, Shriram Krishnamurthi. By the way, I'm on the job market, and Gavin is applying for PhD programs. So if you like what you see in this presentation, come talk to us. All right, so Rust is a language for safe systems programming that is popularizing the idea of ownership types to get memory safety without garbage collection. So if you have a program like this that uses a reference after it's been invalidated, that is unsafe. And if we try to compile it, Rust's borrow checker will flag it as a problem. Cannot borrow v as mutable because it is also borrowed as immutable. So great. Rust is a smashing success story of PL theory transfer to practice. Time to move on. But no, it's not that simple. In survey after survey, we find that ownership and lifetimes are the hardest part of Rust to learn. They actively turn people away from the language. And so if we want to make Rust accessible to a broad audience, then we need to make ownership types easier to learn. And that's exactly what we did, but in a more systematic way than just inventing pedagogy out of thin air and hoping for the best. Instead, we wanted to first understand the misconceptions about ownership that Rust learners had, then use those misconceptions to become the basis of a new pedagogy to address them, and then finally compare the pedagogy against a baseline to evaluate whether it makes a difference. And now let's walk through each step. So first, we wanted to understand misconceptions of ownership. And our orienting principle was to create a test of ownership, like an exam you could give to a learner. And to start constructing a test, we needed a set of problems that represented common situations involving ownership that are difficult for learners. So we looked to Stack Overflow. We analyzed the most frequent questions about Rust to find the ones related to ownership. And they looked like this. Is it possible to return either a borrowed or owned type in Rust? And out of this question, we extract a simplified code snippet that represents the situation. So here, this make separator function wants to return a reference to a string and stir. But in the if branch, it returns a reference to an owned string on the stack, which is not safe. And for each of these snippets, we ask 3 questions to mirror each stage of reasoning about ownership. So first, what error would Rust give for this program? Second, if Rust allowed this program to compile, what is an input that would violate memory safety, if one exists? And third, how would you idiomatically fix this function? And we ask people to justify the latter 2 answers. Now, these are open-ended questions. There's not one correct answer. But for this problem, I would give this as a correct answer. Default does not live long enough. To violate memory safety, we have to call this function and use the output. And a simple fix is to change the output type to an owned string instead of a reference. And in total, we found 8 of these snippets that correspond to these categories of ownership errors. I won't go through them all, but if you've worked with Rust before, they should all sound familiar to you. With 3 questions per snippet, we have a total of 24 questions that form the open-ended ownership inventory, with the term inventory coming from the idea of a concept inventory that's used in education research. And so once we constructed this test, we recruited 36 Rust learners who had recently finished reading The Rust Programming Language, which is a popular open-source Rust textbook. We had them answer a randomly selected subset of the inventory. And afterward, we manually read through all the responses and started to look for misconceptions. So what kinds of incorrect errors did people give to these questions? And overall, what we find is that learners understand ownership syntactically and not semantically. And so what I mean is that learners can successfully predict the compiler's error message in 64% of cases, but they can only write a valid counterexample in 31% of cases, and then only justify it in 15% of cases. And so here's just a concrete example from the data. Like we have one task that uses this code where you have a struct self with two fields, self.getCurve borrows one field, and then this code tries to mutate another field, self.scores. And this is actually safe. This program is rejected due to the incompleteness of Rust's lifetime analysis. And here's one participant's response. They correctly get that there is a compiler error and they understand where it is, but then they attempt to provide a counterexample when none actually exists. And when they go to fix this function, they just throw a .clone on the scores vector, which is totally incorrect. It modifies a copy that gets immediately thrown away. And this is indicative of a deeper trend, where learners' syntactic understanding of an error led them to struggle down the line when trying to fix these functions in practice. And so after observing this data, we felt that what learners needed was a more robust mental model of the foundational concepts of ownership. Specifically, what kinds of undefined behavior are prevented by the borrow checker? And to a first approximation, how does the borrow checker work? Like, why does the Rust compiler reject programs that are safe? And the crux of the issue is the level of abstraction in the conceptual model that we're giving to learners. So the highest level would be like, Rust prevents memory errors. Lower level, maybe Rust enforces aliasing XOR mutability. Below that, Rust uses lifetimes to understand aliasing. And we can keep going. So a formal model describes how outlives constraints relate to alias sets. And then ultimately, a fully concrete conceptual model would literally be the source code of the borrow checker. And what we saw is that learners have a very abstract mental model of ownership. And we think they need a somewhat more concrete mental model. Like not all the way, but something concrete enough to explain the relevant behaviors. And just a note on the terminology, I'm using the phrase mental model to describe the model that exists in people's heads, and the phrase conceptual model to describe the model that exists in abstract formal space. And pedagogy is the thing that turns a conceptual model into a mental model. So we designed a conceptual model of Rust that could explain undefined behavior in the dynamic semantics and unsoundness versus incompleteness with regards to the static semantics. And we reified these models as compiler plugins that can automatically generate a visualization of a Rust program under each model. I'll show you what that means. So this is the visualization we generate for the dynamic semantics. It can take a program like the one you saw at the beginning, where we invalidated a reference to a vector, and it can visualize the state of the stack and the heap at multiple points in the program. Notably, if a program encounters undefined behavior, like reading a pointer after it's freed, we can capture that error and visually represent it. The design is pretty similar to other box and arrow diagrams people have made for C and so on. I'm not going to dwell on it too much. But one interesting detail is that we are executing Rust programs that don't compile, which seems a bit weird. And under the hood, we're using an interpreter for the control flow graph intermediate representation in the Rust compiler, called MIR, which we configure to ignore borrow checker errors initially and then interpret the program until something bad happens. But in terms of pedagogy, the idea is that this conceptual model is sufficient to illustrate what it means for a program to have undefined behavior. But it isn't so detailed as to talk about registers, calling conventions, things like that. Just detailed enough to convey the essential concept. Now, the more novel idea is the static semantics. So here's our other diagram. And the idea is that we can visualize the change in the state of the borrow checker after each line. And we communicate that state through the metaphor of permissions. So this example is almost the same as before, except this code is actually safe because we swapped the order of the print and the push. And now we'll walk through it. So we create a vector v with elements 1, 2, and 3. And the little box on the right tells us that the variable v has gained 3 permissions: read, write, and own. So v is readable, like you could get its length. V is writable, you can add an element to it. And v is ownable, meaning you can move it or drop it. And on the next line, we make a reference num equals and v2. You'll notice this little orange dot, which indicates the expected permissions for an operation. So creating an immutable reference requires read permissions on V, which we have. And in terms of the borrow checker, this operation removes write and own permissions from V, which is because we can't mutate or drop V while this reference is live. And it also creates permissions for num, the reference, and star num, the data accessed through the reference. Because it's immutable, we only have read permissions on star num and not write permissions. Once num is no longer used after the print line, then V regains its write and own permissions. And this shows the idea of non-lexical lifetimes. So the transfer of permissions is related to the live range of a reference and not just syntactic scopes. Finally, we're allowed to push to V on the next line, and V loses its permissions once it's no longer used. And so at a high level, the permissions model provides a concrete way to explain how the borrow checker works without getting into all the details like liveness analysis and lifetime polymorphism. And here's a rough intuition for how it's implemented. We define a permission error on a control flow graph G if some place P needs a permission, like W, at some instruction I, and P is missing that permission at I. And this can be derived from a judgment that comes out of the borrow checker, which we call access error. And the derivation is that access error has a bunch of premises that talk about liveness and reads and writes and conflicts. And our inference rules just shuffle around the judgments, so the entailment proof is quite simple. You can think of permissions as rephrasing the proof generated by the borrow checker in terms of our model, in terms of permissions. All right, so we have our executable conceptual models of Rust's static and dynamic semantics. But as I mentioned, we still need a pedagogy to convert that conceptual model into a mental model. As a base, we forked the Rust programming language, which I mentioned earlier, and we completely rewrote its chapter on ownership using the diagrams like you can see in the screenshot. This is a live public link at rust-book.cs.brown.edu if you would like to check it out after the talk. Put your phones down. All right, so finally, we needed to evaluate whether our new ownership pedagogy actually helped Rust learners. And the basic idea was to run an A/B test. To evaluate Rust learners' understanding of ownership, we used the ownership inventory we developed earlier, but this time it had multiple choice questions, with the key idea being that we based the distractors on common incorrect answers given by participants in the formative study from earlier. To recruit participants, the authors of TRPL graciously agreed to insert this advertisement into the main Rust book where it still stands today. This ad drives about 400 people per day to our experimental fork of TRPL. Then the procedure was that we first added the inventory to the baseline TRPL. We collected participant data for about 6 weeks, and this gives us the control condition. Then we deployed our new ownership chapter, fixed some bugs, and collected data for another 6 weeks. Between those two periods, we had a total of 342 people who completed the entire inventory. And our main result is that compared to the baseline TRPL, the permissions pedagogy improves scores by an average of 9%, which is a normalized effect size of D equals 0.56. So hey, look at that. It's a demonstrable improvement in learning outcomes directly attributable to our intervention. I think that's pretty exciting. And if we dig further, we can find that there were statistically significant improvements on 10 out of 18 questions in the inventory. In particular, the improved questions were primarily either the ones about picking counterexamples or the ones about fixing the code, and not the ones about identifying the compiler error. And we see that as a promising sign, because those were the two kinds of questions we really wanted to help people improve on. There are some threats to validity we discussed in the paper, but I think it's fair to say that our work is helping people better understand ownership types in Rust. To conclude, Rust is cool, but can we do this for other languages? Absolutely. So here's going to be the essential ideas I think you should reuse from this talk. So one is mixed methods analysis. Quantitative data from surveys and Stack Overflow provide a nice way to filter down signal from noise. And then qualitative data from like open-ended exams gives us rich substance to analyze usability and learnability. Another is concept inventories. Targeted multiple choice questions with good distractors are useful in both the formative and summative stages of research to find misconceptions. Modern languages are hugely complicated, and so we have to consciously design conceptual models at the right level of abstraction. And conveying a conceptual model becomes so much easier when you can show and not tell how it works. Conversely, designing your compiler so it can be visualized makes my life a lot easier, just so you know. And finally, A/B testing is great because you can evaluate your ideas with a ton of people by leveraging the resources they're already using rather than needing to continually recruit participants for individual user studies. Okay, that's all I have. Thank you for listening, and let's go make our programming languages easier to learn.
Okay, if you have questions, please come to microphones in the aisles.
Hi, thanks for the great talk. Do you think that there are differences in the types of misconceptions people have if you're thinking about like experienced programmers who are learning Rust versus novice programmers who are like Rust just happens to be their first language? And do you have any like commentary on that kind of thing?
Yes, so in particular, there's both are they experienced or not, but also what languages they've used. The experience of learning Rust, if you know C or C++, is very different. And in practice, we find that people who know C or C++, they understand undefined behavior really well because they see it every day, right? And so they go, oh, mechanisms that mirror the R-safe practices, it's very intuitive to them. But an important factor we've also found is more than half of the people learning Rust are not proficient in a systems language, or at least self-report as such. So I think that's one of the challenging things in designing these resources is you do have to consider the background, but we also have to be practical about who's learning the language, and you can't just target, say, people who already know something about C or C++.
Thank you. This was really a fantastic talk, like really, really fantastic.
Thanks.
I wanted to ask, how did you come up with this conceptual model? Did you just invent it ex nihilo, or do you also have a methodology for coming up with these things? I mean, the ones which work well. Right.
So we came up with the permissions model. Essentially, we were trying to, it was a very iterative design process. I can show you screenshots of 15 different lifetime visualizations that we didn't end up including, and we kept trying to think about it from different perspectives. Ultimately, our guiding principles were, can this particular conceptual model explain the phenomena we care about? And the two phenomena were, when there's an ownership error, can it highlight that error and explain it? And when there's incompleteness, can it give an explanation as to why there's incompleteness? So one notable thing we did not do, you'll see in a lot of other visualizations, is have a visualization of the live ranges of variables as like lines that run through the program. And that was also partly motivated, that was motivated by the fact that those aren't actually fully necessary to explain the phenomena we cared about, but also those are difficult to generalize to cases where lifetimes are non-linear, which does happen in some of the examples we include in the book. So short answer is, a couple guiding principles to say we need to have something sufficient to explain this, plus just many iterations on trying out different visual encodings and seeing what worked.
Thank you.
Okay, sorry, but we don't have any time for questions. Let's take those offline.
Thank you.
And thank Will again.